So why is this relevant? Polymers like HPG possess certain qualities that make them excellent candidates for a drug delivery system in the body. They may be used to attack tumors and have a timed release of drugs. Also, there are serious environmental pollution problems in water from textiles, plastics, and printing industries from their byproducts, and HPG and other polymers may be able to be used to remove the dyes from these industries from the water. So HPG's structure allows for it to potentially be cheaply mass-produced for use in a drug delivery system. The reasons for this, it has a flexible polyether backbone, which ether groups are with the oxygen in the middle, and it also has hydrophilic groups, which make it good in water, and hydrophilic groups would include the alcohols, the ethers, the carboxylic acids. So you can see there's a lot of hydrophilic groups in HPG structure, and it has excellent biocompatibility. It has also shown absorbent qualities of dye in water because of the hydrophilic groups, and it's also not toxic, so it does not add additional pollution. So the experimental background, this experiment used UV-vis spectroscopy, which...
So what are you trying to do then? I'm sorry, I missed that.
That, we'll get to that.
Oh, okay.
Yeah, I got it in there.
Okay.
And then, so I'm using UV-vis spectroscopy, and I'm measuring 3 dyes absorption spectrums, Marchicello, Congo red, and alizarin red. Calculations for a theoretical peak were done using a particle in the box method, which is a model where all of the energy is kinetic. So this experiment, we use different dyes to try and determine whether HPG MA released more or less of the dyes over time, or at least that was the objective originally. And the hypothesis that I made at the beginning of the experiment was that as time passed, more dye would consistently be released from the polymer regardless of the size of the molecule. Smaller dyes would ultimately release the most HPG MA over time. But throughout the experiment, we ran into problems that you will see. So now we're talking about the structures. So I chose Marchicello to be used as the smallest dye. I chose 3 different sizes of dyes just to measure. The goal was to measure the release, how the size affected the release as well. So I drew these in ChemDraw and found by using ChemDraw that the length of the total molecule was 6.8 to 7.8 angstroms. For alizarin red S, it was my medium-sized dye, and this was slightly larger at 11.1 to 12.1 angstroms. And again, I drew that in ChemDraw. And then Congo red was the largest dye, and that was 26.3 to 27.3 angstroms. And so that already leads to a slight room for error, because ChemDraw could only narrow it down to within 1 angstrom of each other. So it couldn't actually say exactly how large or small they are. And this is the structure of HPG again. So you can see the polyether groups, and you can see the alcohols. And then when that turns into a polymer, it changes the structure, which is what we saw at the beginning. So the methods, we determined the different sizes of dyes using ChemDraw, and we made a calibration curve for each dye by making dilutions and then doing UV-vis spectroscopy. And the goal of a calibration curve is to be able to use the slope to determine the concentration of the dyes at any amount. And then we dissolved the HPG using methanol. We treated the HPG methanol solution with each dye, and we took aliquots from diethyl ether every 15 minutes, and we measured the absorption of each aliquot. So here are my spectra values, and I used the equation shown right here based off of the particle in a box model to determine a theoretical wavelength. And the theoretical wavelengths were way off, and I'll talk about why that is. But the equation used the mass of an electron, speed of light, and the number of double bonds in each molecule. And we used, for the length of the box in the model, we used the total length of the molecule, which we determined in ChemDraw. And so for Marcius yellow, I mean, you can see that all of the values were extremely larger than the observed wavelength. Marcius yellow had an observed wavelength of 370 nanometers, alizarin red 340, Congo red 450, and all of their wavelengths in the theoretical were way larger. And that can be attributed to a lot of things, but it's based off of a model, and additionally, it's not a typical alkene. It's an aromatic ring with double bonds, so that changes the formula. So here are my calibration curves, and these I displayed the R squared and the slopes just so you could see the accuracy. So a couple of these are more accurate than the other one, and I put a key here. So the red line, which you can see is on top, is Congo red, and that was the least accurate calibration curve, and I'm not sure what caused that, but apparently some sort of dilution issue. And then green is the alizarin red, and that was a little more accurate, but still not quite what we're looking for. I prefer to have R squared values of 0.99 at least. And then the blue was Marcius yellow, and that was the most accurate one. That was a little more accurate. Issues could have been that dilution samples were too concentrated or not concentrated enough when we took values for their intensity. And a calibration curve, as you see, is absorbance versus concentration, and the slope of the lines is what is used to determine concentrations for any values. So say for instance, if I had a concentration of 0.8 and I wanted to determine how much Congo red there would be, hypothetically I could just go up here and I'd be able to extrapolate the values from the slope of the line.
So your calibration curves seem to follow the size of the molecule as far as accuracy. Is there any correlation in your thoughts chemically?
That's a really good point. I didn't notice that.
Or is that true? That the red is your
the
longest,
red's Congo red,
and that's your least accurate, and the blue is the smallest, and that's the most accurate?
Yeah, that is true. That is true. And then I just took a picture of the Congo red spectrum when I took it over time, and this is just the absorbance versus the wavelength. And the reason I took a picture instead of plotting it, the plot wasn't coming out correctly. So you can actually see where the error occurred here. What happened was we used a diethyl ether.
So what are we looking at now?
We are looking at the combined absorbance versus wavelength from the UV-Vis machine.
For what sample?
For Congo red. Okay. For all of them together. So what we're looking at is you can see step by step here, like I know it's not labeled, but what is occurring here is that the more time passes, the less intense the samples were becoming at the wavelength, at the peak wavelength here, and
remind us what the peak wavelength is for Congo red.
Congo red was supposed to be 450, so you can see it's 450 there, and so what was happening is one of the errors in the experiment was we used diethyl ether as part of as a way to separate and measure the concentration of dye. We wanted to measure the concentration of dye in diethyl ether because it was mixed at the bottom in HPG. So what we were trying to do is I was going to take aliquots of the diethyl ether every 15 minutes and see if there was any dye in that part of it because they weren't supposed to form solution. They were supposed to stay separate. But what happened is we ended up using a diethyl ether that also had methanol in it, and the methanol HPG solution and the diethyl ether with some methanol in it ended up mixing. So we couldn't actually extract aliquots from the